In this third video, let's have a closer look at the augmented Dickey-Fowler test statistic that allows for serial correlation in the errors, but corrects the dynamics by adding lags to the regression. And to make things concrete, let us consider this DGP, where we have an ARP process with a single unit root. How can we find the roots? Well, you can start from this lag polynomial equation. Simply replace the lag operator by z's and then solve for the roots of this equation. Under this formulation, the process is stable if all roots lie outside of the unit circle. We are, of course, interested in non-stationary asymptotics. So let's assume that we have a single unit root. That means that z equal to 1 should be a solution and all other roots should lie outside of the unit circle. Now, before looking into our specific case, let me also introduce some new notation, which will be convenient later on. The sum of these AR parameters will often pop up, and I denote this sum in short by rho. Also, the zeta j's will be useful to rewrite the ARP process. Remember, the lag polynomial pi L is given here by this expression. Now we will use the zetas here to rewrite the AR parameters. In essence, zeta j subtracts all AR parameters from lag j plus 1 onwards. So what is phi 1? Phi 1 is equal to the sum of all the phi's, so the AR terms as of lag 2 subtracted, which is nothing more than the sum of rho and zeta 1, the sum of all the ARs with the sum of phi 2 up until phi p subtracted. Similarly, the higher order phi's can be re-expressed as a difference of two neighboring zetas. So why do I introduce this new notation over here? Well, if I apply this lag polynomial to the process yt, what we get is the regression of yt on its lagged value, and we have p minus 1 lagged differences added to the equation. And that is exactly the augmented Dickey-Fowler regression. The regression that we knew from before is augmented with lagged differences to allow for serial correlation. Now, remember for later on, if we work with a unit root, the lag polynomial at 1, so L equal to 1, is just simply equal to 0. Or in other words, rho, the sum of the phi's, of all the phi's, is equal to 1, just like we have in the previous setting. That means that, like before, we will be interested in testing the null that rho is equal to 1. Now, on the next slides, I will then only look at a simplified setting compared to Hamilton. I will use an AR2, so with p equal to 2 model, and no deterministic components, because it will be easier to understand the intuition behind the derivations without making the expressions overly cumbersome. And getting to this intuition is the most important in these lecture videos. So let's begin. Remember, we have a DGP with an AR2 model, and we would like to test the null of a unit root. Now, under the null, we have a unit root, so rho is equal to 1, and we can simplify the expression over here. So we start from the DGP, under the null, rho is equal to 1, which becomes this guy. Now, if we bring now the lagged y to the other side, we have the difference of yt. And if we also bring that guy to the other side, we have the lagged value of the difference, which is nothing more than this. If I now pre-multiply both sides by this inverse, you can verify in Hamilton that you actually get this infinite sum of the error terms. Or in other words, under the null, the series in differences is stationary. It actually can be written as a linear process. Now let's estimate our model where we have a lagged y and a lagged difference as a regressor. Under the null, we have rho that is equal to 1, and I use here this convenient matrix notation. How does our OLS estimator look like then? Well, nothing more than the standard formula x prime x inverse times x prime y. We plug in the DGP under the null, so the expression for y under the null, to arrive then at our key expression, estimator minus the true population parameters. And we need to look for the appropriate asymptotic rate of convergence, as we always do. So we need to introduce the appropriate scaling to get the probability limit of x prime x or in x prime x inverse. And we need to introduce the appropriate scaling for this cross product to converge in distribution. So let's start with the scaling of x prime x. Start with x prime x on this slide. And let's expand it. So just plug in the definition of what x is. We have the sum of the squared y's, the sum of the squared errors on the diagonal, and then there is the cross product term here on the off diagonal. Now we know that we need to look at all elements individually and introduce the appropriate scaling. Now for the upper left elements that we did already on some slides, videos ago. We needed to have 1 over t squared for that guy. And we did the work already over here. For the sum of the u squared, this is a classical term. By the law of large number, that one goes to gamma naught. So the only new term actually is this cross product, where I immediately introduced the scaling already. Let's verify the scaling. So let's plug in the DGP for yt minus 1, which is nothing more than yt minus 2 plus our error term. And then I expand the terms, and we are left with this expression, which is the cross product of y and u, which are separated 1 point in time, and another sum of the squared u's. Now, we verified this limiting distribution also a couple of slides back already, as you can verify. I put it here immediately on the slide. Now that we have obtained the appropriate scaling for all of the terms, we are ready to introduce our scaling matrix epsilon that ensures that each entry receives its appropriate scaling. And to set up the scaling matrix, you look at the powers of t you need for the elements on the main diagonal. The scaling for the off-diagonal elements will then follow by definition of setting up the scaling matrix. And either they will be exactly the scaling that you need for them to also converge, or you will have too much scaling. And in that case, those terms go to 0 in the limit, as you will see here or in the tutorial assignments. So we set up the scaling matrix. I introduce the appropriate scaling based on the terms here on the diagonal. And I've already put the limiting distributions in place Note that we have too much scaling on these off-diagonal guys, so they go to 0. Finally, we also use the upsilon, the scaling matrix, to introduce the scaling for the cross product of X and the error terms. You can check for yourself that this limiting distribution then follows. How do we put all pieces together? Well, we blow up the left-hand side with our scaling matrix. And we also introduce then the scaling matrix to the right-hand side, as we did a couple of weeks back. Then I pull out the trick over here that I insert the scaling matrix and its inverse in the middle, which I can do since this is the identity matrix. And next, I pull in the scaling matrix inside of the inverse. So this guy goes inside the inverse, this guy goes inside of the inverse, which I can do if I also take their inverses. And then I only have this guy left for the second term. On this line, there's actually no new information, but just putting all results from the previous slides together, and we derive the limiting distribution of this guy. If you then just combine both pieces, then you arrive at the final limiting distribution. Now, this is all not that interesting, but what is more interesting is whether we can actually do inference with this test statistic. Again, this test statistic, so the upper part over here, contains nuisance parameters, lambda, sigma. So no, we can't directly simulate from this limiting distribution. What if we don't use this statistic to do inference, but the regular t-statistic instead? I'll start from the definition of the t-statistic, where I make use here in the denominator of this new notation, where I extract the first element, so element 1, 1, out of this cross product matrix, since I'm interested in doing inference also on the first parameter, the row in the model. The numerator is exactly the test statistic from the previous slide. What is the new ingredient popping up over here? Again, that is the sample variance of the residuals, which converges in probability to sigma squared. Now, in the denominator, we have the first entry of x prime x inverse that is blown up by actually t squared. If we look back at the scaling we introduced for this cross product matrix, we see that that actually corresponds to exactly scaling 1 over t squared. Now, of course, we need to have the inverse of this matrix. And since x prime x had 0 off-diagonal elements, we can very easily compute this first entry in the inverse matrix over here. It's nothing more than the lower right entry divided by the determinant of the cross product matrix, which is in this case just the product of the diagonal elements over here. Now, what happens if we put all of these pieces together? We see that the nuisance parameters in the limiting distribution of this regular t-statistic do nicely cancel out. And we are left with a regular limiting distribution that is free of nuisance parameters. So that is very nice. How can we use this augmented Dickey-Fuller test in practice? Well, in practice, we of course do not know how many lagged differences that should be added to the test equation. So what you can do is use information criteria such as BIC, for instance, to determine how many lagged differences should be added to the test equation. And these lag differences are added to allow to capture serial correlation in the error terms. And we can just rely on the regular Dickey-Fuller distribution here to do inference.